Everything.
Alright, you know the normal routine.
Yes, starting from you. Come, face me here. When I say Tera, what is the standard form? If you open that book,
she's correct. She's correct.
thanks for our. All right, can I have your seat? Bolu. All electromagnetic waves has, give me just one specific property of electromagnetic waves. Property of electromagnetic waves.
Can I bail out?
Not bail out. All right, bail out.
Light bail. Light bail
Properties.
I'm going to class. I don't know if you do them.
Oh. Aminat. Were you in the first class? Yes.
No, now we would be.
Rejoice. Amina was not in the first class.
Yes, in the one class.
Okay. That means this is your own question, Rejoice. I said the propagation of water wave is being done in the laboratory using what equipment or apparatus? The propagation of water wave. You did not answer your question. You want to answer our question? All right.
I'm not going to answer that.
Me, I gave you that one.
No, what is the one? Well, that's like you drew like stuff like this. Is that not it? What's that one for? Don't tell us. I think it was like, what is not fair?
Hey, Amina, your question. What is the speed of light? What is the value for the speed of light? Don't bail her out. Let her bail herself. Yes, bail yourself. Amina. Notification. Hello. No noise. Three of you. You should have stayed home and sleep. I said, what's the value for the speed of light? All people that were not in the class, be able to answer. Don't talk. I gave you your own question, you don't know it. Don't try. I gave you your own question, you don't know it. No. Bail yourself out before you bail out. So, three of you remain standing. Yes, stand up. You. Hello, no noise. Yes, for you. What are the two distinct regions in longitudinal waves? Yes. What are the two distinct regions in longitudinal waves? You guys don't read at all. You just write. You just write and forget the notes. No be you go tell me wetin I go do. So you don't know too. Okay, remain standing. What are the questions? Solutions to assignment. Yes, assignment.
Even if why longitudinal wave travel by 180 degree or 0 degree.
Yes. Who did the assignment? Who did the assignment? Let me see. Hello, let's be fast now.
Oh yeah.
We still have something to do.
Travel by 0 degree or 180 degree because the particles of the medium vibrate parallel direction of wave travel.
That's not what I want. Yes. And I want you to be specific. Pick one.
Do you know? That's sure.
Yes. What did you do, Jari? Let me see your own assignment.
What I just told you is what what they are doing. What is it? Wait, you know what? I know what you guys are doing. It's like travel by 0 degree because the particles of the medium vibrate.
Why did you pick 0 degree?
And I'm not sure. The particle of the medium.
You are repeating what I gave you. Yes.
No, you don't give us assignment. Assignment.
What did I give you as definition for longitudinal wave? Let me see. Let me see now. Why you can't see?
I'm not answering the assignment. I'm not answering. I'm like to do one of
Yes, let me see your own bolu. It's the same thing. You just copy and paste.
No, this is assignment together.
This is the assignment together.
Yes.
It's copy and paste now.
No,
It's still copy and paste. I mean,
the same thing.
same thing. Esha and Co. No one at the three of you are standing. All right, give me the calculation question. Hello, no noise, please.
Okay.
What is the question?
Radio station broadcast at a
Frequency of what?
200
Hello, if you talk, you go outside.
frequency is equals to 600 kilowatts.
600 kilohertz. Yes.
Speed of light. Calculate the wavelength of the radio wave.
Speed of light.
3.0 times 10
What's the SI in Bolu? Are you Bolu? All right. What other parameter were we given? Okay. Then what are we looking for? So what's the relation? V is equals to what?
F lambda.
F lambda. Then divide both sides by F. So lambda is equal to what? V over F, which is equal to what? 600 times 10 raised to power 3, a big kilo, over what? 3 times 10 raised to power 8. So if we have 3 here 1, we have 3 here. So this is more or less like saying hello. Hey. Things have become like this. Appear on the live, so that you can see that you not read your book. Come here, come and stand here. No, don't stand at the back. Come and stand here, so that everybody will see you. And don't cover your face. Stand here, stand here. Hello, come like this. 1, 2, 3. Face me like that. Face me. Come here. Good. Rejoice. I must be seeing your glasses. All right. So times 3. Then converting these two indices, we have what? Times 10 raised to power minus 8. Is there any magic there? Any magic? So we have 200 times 10 raised to power minus 5. And don't forget, this is also 2 times 10 raised to power 2 times 10 raised to power minus 5. 2 minus 5, we have 2 times 10 raised to power minus 3 what? Yes. V over F. Okay. So if we, where's the duster? That is true. So this is supposed to be 3 times 10 raised to power 8 over 6 times 10 raised to power 5. Having 3 here 1, 3 here 2. So we have 10 raised to power 8 times what? Times 10 raised to power minus 5 over.
So you wrote 10 raised to power, right? 10 raised to power 8
So this is what? 8 minus 5 over 2, which is what? Which is what? 500. 500 what? So lambda is equal to 500 meters. So who got this? Look at my senior. Simple question. I'm a show. All right. Is there any other question?
Yes.
Who got this one?
We got it.
Oh, it's a video Shanko. Good.
This one I got it.
Yes. The other question. The equation. Yes. Y equals what? 5 sine what? 3x minus 4. We are looking for frequency. what? So what is the normal wave equation? Y is equals A sine what?
WD plus or minus 5.
It's fine that you don't know. You're asking what's the name? Y is now equals A sine what? 2 pi ft, having plus or minus what? 2 pi f over. So y is also equals A sine 2 pi, yes, 2 pi ft plus or minus what? X over lambda. So I think we can compare and contrast from here. So what are we looking for? Okay, we can say y is equals A sine, hello, pay attention, 2 pi into brackets ft minus x over lambda. I mean, comparing directly to this one, so we can say minus 4 is equals to what? Minus 4 is equals to what? Is equals ft, having, and also we can say 3x is equals to what? Minus x over lambda. So this is 1. So we can say x cancel x, having, then lambda from here will be what? Will be what? Minus 3. Minus 3 what? You don't understand? Those of you that were not in the previous class, I do not expect you to understand. This is for those that were in the last class. So I said we do what? Direct comparison. Y is equals 5 sine what? Sine 3x minus 4. Abby? Hello, pay attention. So now we have to make this one look like this one. So from here now, there's x here and there's also x here, Abby. And don't forget, the sign is also moving with this one. So we can say minus x over lambda is equals to what? 3x over 1, Abby? Yeah. Cross multiply, we have what? Minus x is equals to what? 3x lambda, Abby? Divide both side by x. Divide both side by x. This one cancel this one. This one cancel this one. So we have what? Minus 1 is equals 3 lambda. Divide both side by 3. It's even 1 over 3 itself. So lambda is equals to what? Minus 1 over 3. What's the decimal form? 0. What? Lambda is equals minus 0.333. Abby? And that is in what? Meters, Abby? Meters or centimeters. Now, what else are we looking for? What are we now looking for? We are looking for frequency and so from here we can say V is equals what? F lambda, Abby? Hello. Given that V is equals what? F lambda. let's make f the subject. So f is equals to what? V over lambda. So we can make direct comparison here. We can write this one now. We write it as y is equals a sine 2 pi into brackets what? Vt over lambda minus x over lambda. Is there any confusion? Remember, I will say V is equals F lambda, Abby, and you make F the subject of the formula to substitute for F here. So once you substitute F in this formula, you get this. F becomes V over lambda, and that's what we did here. So we can say, is there any question? You don't understand this thing? That's wave equation for you. It's always confusing, but this thing is straightforward. From, let me, okay, is it because there's too much equation on the board? You shall know how we got here from this place, Abby. Now we now said, remember your normal formula that we use here, V is equals F lambda. So we say substitute for F in this formula. So we can make F the surrogate formula. F is equals to what? V over lambda. Abby? See, she's talking. V is equals to what? F lambda. Then we make F the subject, which will be what? Divided by lambda. We have F is equals V over lambda. Then we substitute the value of F here in this equation. We are removing this F now and replacing with what? V over lambda, and that's how we got this. Is there any question? Now after this, we can now say the value for our V can be written as, okay, let's bring out lambda. We have y is equals a sine. Who's making noise with that pen? Vt minus x. Hello? Vt minus x. So from this equation now, we can say Vt is equals to what? Vt is equals minus 4. Abby? Let me see the question. Did they give us value for t? Okay, they said represent a wave motion. That means you are not looking for an actual answer. Whatever you are getting will be in what? In wave equation. Will be in what? Wave equation. Like this now, V here is what? V is equals minus 4 over t. That's what you have as V. Then what else are we looking for? Frequency, having. Then period. So our frequency is now what? V over lambda, which is equals minus 4 over t divided by what? Minus 1 over 3. Abby? F is now equals to what? Minus 4 over t times minus 3 over 1. Minus times minus plus. So we have what? F is equals 12 over T. Abi? Now, period. Period is what? Period is 1 over F. Abi? So we can say 1 divided by 12 over T, which is equals 1 times T over 12, which is equals T over 12. So our T now, which is period, is the what? Time over 12. So now if we want to rewrite the equation, hello, can I clean this one? If we want to rewrite the equation, remember our equation is y is equals, what is the simplest one? What's the simplest one? Or let's say let's use this one that we derived here. This one. We know that our a from this equation is what? Is 5, Abi? We can now say 5 sine 2 pi over, what did we get as our lambda? We can just use 0.33, Abi? Minus 0.33, open bracket what? Let's represent this in fraction. Minus 1 over 3, Abi? We'll come back for this. So VT is what? VT is minus 4. Abi? VT is minus 4 minus, what is X? What is V? V itself is what? So we have minus 4. Then minus what? Minus x and 3x. Minus x and 3x. X equals to 3x. To cancel out. Leave it at that. Since this is the waveform, let's leave it at that. So our lambda is what? 0.3 minus 0.33. Then our what? Our f is equals 12 over t. Then t over 12. Let's leave it at that. So who got this one? What did you do? Let me see what you did. Three Musketeers. What do you people do? You did not do it. This is SSC question. I picked it from your textbook. New school physics. Yes, new school physics. So I think that will be the end of the assignment. You can put this down. You cannot sit down. All of that lady. Yeah, come on, sit down, come on. All right, stationary or standing waves. Put this down first. Hello, no noise. Stationary or standing waves? Stationary or standing waves? Do you put down that? Stationary or standing waves? When two progressive waves? When two progressive waves? Before we comment, I said stationary or standing wave is what form of wave? Thank you. Transverse wave. When two progressive waves of the same amplitude and frequency. When two progressive waves of the same amplitude and frequency. When two progressive waves of the same amplitude and frequency are traveling in opposite direction. When two progressive waves of the same amplitude and frequency are traveling in opposite direction, comma, the resulting wave is stationary. The resulting wave is stationary, full stop. The resulting wave is stationary, full stop. There are two regions. There are two regions. There are two regions associated. There are two regions associated with stationary waves. There are two regions associated with stationary waves, which are one node, NODE, one node. Then two, antinode. Hello. So for this, we have at this point. Hello, stand up. Stand up. At this point, we have the node. At this point, we have antinode. At this point, we have another node. At this point, we have antinode. Okay, opposite direction. So this one will move like this. Antinode. Then this will move like this, like this. So this is antinode, antinode, node, antinode, antinode, node. So from this point, hello, from this point to this point, how many wavelengths do we have here? Yes? From this point to this point. So we have lambda over 2. Now from this point to this point, we have what? From this point to this point, we have what? Lambda over 4. Thank you. Now from this point to this point is now what? We have lambda over 2 plus lambda over 4, and this is what? What's the LCM? 4. So we have 2 lambda so we have what? 3 lambda over 4, lambda over 6 nikoko. So that is that. You can put that down. Sit down, sit down. Like, continue talking. I still say shut up. You call me and come and shout 15 hallelujah. Hallelujah 15. But looking at that question 2, that solution, in some other cases they'll give you the value for the t. Are you getting it now? But that question was a theory question. They wanted to see the form in which the wave will take. They wanted to see that t there. You know, some people, as they got to that stage, they'll be confused. They won't know what to do. They just stop halfway. That's what they wanted to test. So, in some other cases, like if it's UTM will give you value for t. And once you have value for t, that becomes a piece of cake. So for the node now, let's discuss about the node. So in this case now, you can say one circle, one small circle is what? Lambda over 2, and half of that circle is what? Lambda over 4. Abi? Because from this point now to this point, half of the circle is lambda over 4. Or the full circle up and down is what? Lambda over 2. Take note. This thing, this one go take note because we'll be using it in subsequent questions. So you escaped the question. You escaped. You had a call. I see. Node. Remember, we have two distinct region of the standing or what? Stationary wave, which are what? Antinode and node. So now we are talking about node. Node. This is a point. This is a point. This is a point. This is a point along a stationary wave. This is a point along a stationary wave where there is no movement of the wave particles. Where there is no movement of the wave particles. This is a point along a stationary wave where there is no movement of the wave particles. Or medium, where there is no movement of the wave particles, or medium. If you are following us live, you can like, comment, and share. Subscribe. Yes, don't forget to subscribe. Alright. So, at this point, continuation, at this point, the wave possesses maximum potential energy. Yes, you say, welcome. Stand up. Cannot escape the judgment of the Lord. You sit down. You're not regular customer. Sit down. I know regular customer. This one is regular customer. Yeah, on la ferry. Alright. No noise. Let's continue. At this point, there is maximum potential energy. What is potential energy? PE is equal to what? mgh, Abby. Now, at maximum potential energy, what value is that? At maximum potential energy, what value do we have? See, they are looking at me. At maximum potential, that boy on Ankara, stand up first. Stand up, come. I'll tell you something. I said at maximum potential energy, what do we have? What value do we have? 0. Sit down. It's gonna save you. So now, hello. The node now. They are telling us at the point of node there is maximum potential energy. Look at this point. This point is the what? Is the main position. If you have your Cartesian plane, your x and y plane, and that middle is what? 0, 0, having. That is the main point. There is no movement there. Are you getting it now? So at every point of a node, there is what? No movement. That is, there is maximum what? Potential energy. Are you getting it now? Alright, antinode. 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 This is a point. Antinode. This is a point. Rejoice. You are just rejoicing up and down. Okay. This is a point along a stationary wave. Hello, no noise. This is a point along a stationary wave where there is maximum movement of the wave particles. Where there is maximum movement of the wave particles or medium. Where there is maximum movement of the wave particles or medium. Full stop. At this point, antinode. This is a point along a stationary wave where there is maximum movement of the wave particles or medium. At this point, the wave possesses maximum kinetic energy. At this point, the wave possesses maximum kinetic energy. At this point, the wave possesses maximum kinetic energy. This is where you have your what? Your maximum displacement. Hello? At this point, you have your what? Maximum displacement, which is your what? Maximum displacement is what? Thank you, amplitude. Maximum displacement is your amplitude. Amplitude. So that is your maximum kinetic energy. So either upward maximum displacement or downward maximum displacement. What is the upward maximum displacement in transverse wave? Crest. Downward maximum displacement. Sure, thank you. I want to feed you skip. Oh, then normal. Upward maximum displacement is crest. Downward maximum displacement is trough. Ça va bien, merci. Et vous? All right, let's take one or two questions. Now, this one I'm giving, that information I gave last. Hello, that information I gave last. Maximum downward displacement. So this is your trough, and this is your crest. So it is part of what we have discussed in previous class. So it is part of what we have discussed in what? In the previous class. For those of you that are just joining the live YouTube view, So this diagram now, using the diagram above, hello, no noise. Find the wavelength of the waveform. Using the diagram above, find the wavelength of the waveform. How do we approach this? Why are you always facing? Come and sit here. Come and sit here, Joe. VVIP, come and sit here. Come here, come. Oh, really, more everybody, come. Sit here, don't. Ẹ ṣe ìyá jọ, hallelujah. Ẹ̀sùn dáadáa, ẹ̀sùn wọlé. Ẹ wọlé kanlẹ̀. All right. Please pass her bag. Everyone pass bag on. Bag on, see front. Hello, no noise. Yes, how do we go about this question? Yes. Remember, I gave you this. Abi? And what did I say this is? The full circle is what? Lambda over 2, Abi? And how many do we have here? 1, 2, 3, 4, 5. So, to find the wavelength, we say lambda over 2 times 5 is now equals to what? The full length is what? 18 centimeter. So this is what? 5 lambda over 2 is equals 18 over 1. Cross multiply, we have what? 5 lambda is equals 18 times 2, 36. The other side by 5. What do we have? 7.2 what? So this is 7.2. Lambda is what? 7.2 centimeter. Since the length is in centimeter. Is there any question? This is what UTM will give you. Something like this. They also look for the wavelength. So you don't need to write. You can just do it from here. Shall I give you another one? A quick classwork. Thank you. You see now, as we are not there now, who will give me the duster? Can I clean this? No mind, just be serious. Don't mind him. Neglect all forms of distraction. Don't let him distract you. What kind of wave is this? To start with, what kind of wave is this? So, waves in pipe. Thank you. This is how waves in pipes look like. Don't worry, as we approach sound, you know the difference between wave in pipe and other types of waves, or other examples of waves. So, this is the question: what is lambda? Find lambda. Yes, now this now. It's classwork. Yes, quick classwork. Quick classwork. Find lambda. Some people have gotten their. Solve your own too. Solve your own. Bolu, what did you get? I like your drawing. Have you gotten it? Please don't joke with this thing, oh. Alright. Amina, what did you get? Amina, micro solving, don't she micro solving. Bolu, look at me. Má solve sẹ́yìn ìwé, solve sínú ìwé. Solve sínú ìwé. All right. You have 1 minute more. 1 minute more. You have 1 minute more. Yes. Alright, yeah, Joe. How did you get? Hey, how did you get it? You solved it. Let me see. Let me pass our book. She's not your friend, but you guys came in together.
Sir, just do what you want to do. See, she's confusing anybody here.
Okay? Give it to her, give it to her.
I don't understand.
Yeah, give it to her now. You don't need to understand. You will let some cancel Ben. Alright, let's do it together. Please pay attention. Hello, pay attention, pay attention. Thank you. So this one now is lambda over 2, right? Right? Another lambda over, then this is lambda over what? Lambda over 4. So we have lambda over 2 plus lambda over 2 plus lambda over 2 plus lambda over 4 is now equals to what? 14. Abi, LCM is what? 2 in this, we have what? 2. So we have 2 lambda plus 2 lambda plus 2 lambda, then plus what? Plus lambda is equals 14. 14 times 4, we have what? So 7 lambda is what? Is equals 56 divided by 7 divided by 7. Lambda is equals to what? 8 centimeter. Is there any question? Is there any question? Madam, is there any question? Alright. Moving on. You can put this down. Is there any question? Those of you sitting at the back, is there any question? Madam? Yes, what's the question? Let's it out. I said lambda over 2, lambda over 2, lambda over 2, lambda over 4. Sum it up. So this now is what? 2 in 4, 2. You look for the LCM.
It's just like 7 lambda over 4 equals to 14.
Okay, this now 2 lambda plus 2 lambda plus 2 lambda plus lambda, that's 7 lambda. You cross multiply. Okay, I get your question now. Now you equate all of this to this, since they are equal. The sum of this is equal to what? To the length. Are you getting it now? So if you sum this up, you equate it to the length, then you get what you are looking for. Have I answered your question? Examples of stationary waves. Examples of stationary waves. Examples of stationary waves. 1. We have stationary waves in string. Examples of stationary waves. 1. We have stationary waves or stationary transverse waves in string. Stationary transverse wave in string. Stationary transverse wave in string. We have something like this. String. Where you have 2 nodes. one node here and another node here. And this is your antinode and antinode. Stationary transverse waves in string. Hello. Stationary transverse waves in string. Then you draw that. You know when you pluck a string on the guitar, this is what you have. You have the string going up and down, forming something like this. So that's the first example of stationary waves. Then the second one, Rejoice. No, you borrow me your glasses. I want you to view this writing. I can't. Oh, so that I'll fall down, Harry. All right. Now, there's difference between there are two examples of waves in pipe. There are two examples of waves in pipe. This one is a closed pipe. If you see one side closed, it is what? A closed pipe. But if you see the two sides open, that's an open pipe. Take note. Take note. Because when we approach sound wave, we'll be taking two different formulas for open pipe and closed pipe, so you won't mix them up. Are you getting it now? So if the two sides are open, if you have something like this now, if you have something like this, then you have the wave inside like this. Then let's say you have something like this. Now this one is an open pipe. Are you getting it now? The two sides are what? Open. You know, it's normally in your tap, the pipe is directly into the borehole, having, and it is opened. But you at the extreme end, having, this side is open to the borehole. This is the side you lock. So if you want the water to come out, you open this side, having. That is why it is called what? Open pipe. Do I make myself clear? Is there any question? So those are the two types of waves in pipe we have. We have waves in open pipe and we have waves in what? Closed pipe. So the second example of stationary waves, we have stationary longitudinal waves. Stationary longitudinal waves. Stationary longitudinal waves. Stationary longitudinal waves in an open pipe. Stationary longitudinal wave in an open pipe. Stationary longitudinal wave in an open pipe. Stationary longitudinal wave in an open pipe. So this is the node, this is antinode, 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 antinode. Hello, no noise. Yes, right. Stationary longitudinal waves in an open pipe. Something like this. Yes, right. Anything I draw. If you do not draw, it's at your own peril. Are we done? Hello, no noise. I'm normal rope me. I'm at the location. Then another one, which is the third example under stationary waves. We have stationary longitudinal waves. Stationary longitudinal waves. Stationary longitudinal waves in a closed pipe. Stationary longitudinal waves. Stationary longitudinal waves in a closed pipe. Remember what I said about closed pipe? Stationary longitudinal wave in a closed pipe. So this one is going like this and this one is going like this. So this is the node. This is the node and this is the antinode. So you can draw that also. Stationary longitudinal waves in a closed pipe. Now, stationary wave equation. The wave equation for stationary wave is a bit different. It is a bit different from normal. Can I rub this up? Hello? Stationary wave equation. Hello, no noise. We have y equals a sine omega t. Hello, this is the difference. So we have this to be equals y is equals a sine omega t. And remember, our omega is what? 2 pi f, Abby. So our y becomes what? Why are you guys standing? A sine what? 2 pi f t. So that is what the equation becomes. So let's take a question under this. Come and sit here before I knock your head. Sit here. We talk to my party class in Lily. Take down this question. So wait, after you are walking up and down, check something, always checking something. Aminat. Don't let our power bank fall down. The displacement, put down this question, the displacement of a standing wave is given by y is equals 8.12 sine 12.5 t. Y is equals 8.12 sine 12.5 t. The displacement of a standing wave is given by y is equals 8.12 sine 12.5 t. Where y is in centimeter, and t is in second. Full stop. Determine one. The amplitude. 2. The frequency of the wave. Simple, like ABC. Quickly do that. Ça va bien, merci. Quickly do that. No, me, do it. You compare and contrast with the formula. You compare and contrast the formula with the equation given. You compare this and this. Abi? Compare this and this. Simple. What is A from here? What is A? And now 8.12. That is your A amplitude. Then you solve the other one. Yes, that's the amplitude. Jim Asun, stand up. Keep moving. Do like this. So what do we have? Who is saying pi is 3.44 there? Oh. So in the last class, I gave you pi is 3.44. What is pi? That's what I gave you in the last class. I don't know. What is pi? I'm asking people that were in last class. What is pi? What did I tell you pi is in last class? Pi is semicircle, and what is that in degree? So why is you saying 3.142 is correct? Shama won't hear. Okay, I have another sweet question. Take that home as assignment. Sound theory. Introduction. That's assignment what? Yes, that question. Take it home as assignment. We are going to introduce sound theory today. You have done what? The question. I'm not ready to solve. Take it home as assignment. Go and visit it again. Play with it. Introduction to sound theory. Take it home and play with it. So I'm going to introduce you to sound theory today. Hello? Sound theory. Hello, pay attention. In the previous class, I said sound wave is being propagated in the laboratory by what apparatus? Using what apparatus? Sound wave is being propagated in the laboratory using what apparatus? Sound wave. Who said mechanical flash? The one on it can always be you. Thank you. Tuning fork. Ceiling fan, no. Tuning fork. Tuning fork. Yes, ma'am. I said water wave is being propagated in the laboratory using what apparatus? And you are telling me tuning fork, and you are claiming right now. Water wave. Is water wave same as sound wave? No. Imagine, I'm asking water wave. You are giving me answer for sound wave.
I can't answer.
I will store you the slippers. You said something. Oh, JB. Should have kept quiet. Oh, in our village we don't eat half bread. Yes, ma'am. So this is what the tuning fork looks like. Hello? No noise. So let's start. Sound theory. Sound theory. Stand up, stand up, stand up. You did not get the question. And you are still talking. Stand up. Stand up. Stand up. Stand up. Stand up. Stand up. So that thing cannot wait till after the class. Let's do it after the class. Hallelujah, mommy. Sit down. Sit down, Joe. You go out of the classroom. Sit down. Come. You are still talking. Carry this dust down your head and come and advertise. Come and advertise for us. Hello. Should we end the class here? No. So why are you talking? Rejoice, sit down. Sound is an acoustic wave. Sound is an acoustic wave. If you like, draw. If you like, don't draw. It's your cup of tea. Sound is an acoustic wave which travels. Sound is an acoustic wave which travels through elastic medium. Let's put that through an elastic medium. Through an elastic medium. Sound, that's full stop. Sound can be divided into two parts. Sound can be divided into two parts, which are one, noise. Ariwo, noise. Two, musical notes. One, noise. Two, musical notes. Now let's talk about noise. Hello, you guys are making noise. Now let's talk about the noise. Let's talk about the noise. Noise is the combination of sound. Noise is the combination of sound. Noise is the combination of sound produced by two or more sources. Not if you start. Noise is the combination of sound produced by two or more sources of sound. Sources of sound. It is the combination of sound produced by two or more sources of sound vibrating at irregular frequency. You stand up there. You just leave the class. Vibrating at irregular frequency. Vibrating at irregular frequency. I go again. Noise is the combination of sound produced by two or more sources of sound vibrating at irregular frequency. When this one is talking, that one is talking, that one is talking, another one is talking. You guys are producing what? Noise. But from different what? Sources of vibration. Are you getting it now? Now this one voice might be very tiny. That one will just use bass voice. Happy way is there. So that is what different what means or medium of Propagation. Are you getting it now? Different sources at which the sound is being produced. So now the fact that this one voice is tinier and this one voice is what? Is very deep. Are you getting it now? It produces what? Irregular frequency. The frequency at which they are being produced is what? Different. Are you getting it now? And due to irregular frequency, we have what? Noise. Is there any question? Any question? Let's take down musical notes. Musical notes. Aminat, you are not sitting upright. Always charging, always charging. Always charging, always charging. Don't let our power bank fall down. Alright, musical notes. Musical notes. Musical notes. This is the sound produced by a source. This is sound produced by a source of sound. This is the sound produced by a source of sound vibrating at a fixed or regular frequency. Vibrating at a fixed or regular frequency. Vibrating at a fixed or regular frequency. Now, characteristics of musical notes. Characteristics of musical notes. Characteristics of musical notes. One, we have pitch. One, we have what? Pitch. One, pitch. Two, quality. Quality or timbre. Quality or timbre. Then three, we have intensity. Intensity or loudness. Intensity or loudness. Intensity or what? Intensity or what? Loudness. Thank you. Thank you, thank you, thank you. That is the loudness. No. Don't mind that, don't mind that, don't mind that, don't mind that. Intensity or loudness. So now let's talk about the pitch. Hello. Let's talk about the pitch. This is the character. She thought she's still at Eric Korodo. This is Akada X. This is the character that distinguish. This is the character that distinguish a high note. This is a character that distinguish a high note from a low note. This is a character that distinguish a high note from a low note. In normal human beings, if you see someone that is very big, you know this person's voice, oh my shaking it, oh my thick. But if you see someone that is very tiny, you can't expect someone that is very tiny as she is now. She's a bit tiny, but not very tiny. Your voice is tiny. But you can't compare your voice with that of That bros that is sitting at the back.
No, it's a guy now.
Oh, now it's a guy.
The guy.
Okay, can you compare your voice with our voice?
Chica. No, no.
Why?
My voice is not sing now. My voice is not sing.
So normally, due to the size, you expect people that are bigger to have bigger voice box, or what we know as what, pharynx. Yes, pharynx. Is that what a science then?
Yes.
Is it a science then?
Yes.
Was a science then? It was a science then, or he is a science then? So people with is that alright?
Yes.
Okay. Sit down now, sit down. So originally you expect people with what? People that are bigger to have bigger voice box, and people that are smaller with what? Smaller voice box. So those with bigger voice box has tendency to have what? Louder or voices with low notes. Are you getting it now? While those that have tinier voice box are meant to have what? Higher notes. Their voice are of what? Higher notes. Hello? So what distinguishes the high note from the low note is known as the what? The pitch. Are you getting it now? For those of us that attend choir rehearsals, the choir master will say, high pitch, high pitch. Low pitch. Something like that. So now the pitch distinguishes a high note from a low note. Are you getting it now? Now let's move to the second character. Quality or timbre. Timber. It's not Timberland. Quality or what? Timber. This is the character. Quality or timber. This is the character that differentiates. This is the character that differentiates between notes. It differentiates between notes produced by two instruments. It differentiates between notes produced by two instruments played at the same frequency. Played at the same what? Frequency. Now, let me cite an example. Maybe you have an old drum set. If you raise that hand, I'm more direct in there. I'm there. So we have an old drum set and a new one. Are you getting it now? Now, if you should play the both of them at the same frequency, will there be a difference in the quality of sound produced? No, why? Depends on the drum. Somebody, let me give an up. Let me stop it. If yes, why would there be a difference? The old drum and the new drum. The old drum, the quality has what? Thank you. That's what I want to hear. The quality has what? Reduced. It's like this part of the class, they are contributing more than this part. This part, So now, the quality of the drum, that's the old drum, has what? Reduced. So that is what we are calling what? Quality or what? Timber. Do you get it now? Yes, it is RE. It's not Timberland. Timbri, Timbolo. Alright. So let's continue. It depends on the harmonics. Full stop. It depends on the harmonics. It depends on the harmonics or the overtones. It depends on the harmonics or the overtones present in the notes. Or the overtone. Harmonics. Overtone. Notes. N-O-T-E. Notes. Musical notes. So, I say it depends on the harmonics or the overtone present in the notes. Full stop. Overtones, I want to give you a brief explanation of what overtone means. Overtones, who left the class? Overtones are integral multiples. Overtones are integral multiples of the fundamental frequency. Overtones are integral multiples of the what? Fundamental frequency. Quick question. Yes, write it down. Which of the following? No, don't write it though. Just look at me. Which of the following? Yes, look at me. Which of the following is not an overtone? Which of the following is not an overtone of 250 Hz? Which of the following is not an overtone of 250 Hz? A. 500 Hz. B. 1000 Hz. C. 1200 Hz. And D. 2500 Hz. So from the definition I gave you of overtone, which of the following is not? Because it is not what? A multiple of the fundamental frequency. Do you get it now? So C is the correct answer. Intensity or loudness of sound. The last part. Right here now. Intensity or loudness of what? Sound. Intensity or loudness of sound. The intensity of a sound. The intensity of a sound at a place. The intensity of a sound at a place. The intensity of a sound at a place is the rate of flow. It is the rate of flow of sound energy is the rate of flow of sound energy per unit area. This is the rate of flow of sound energy per unit area perpendicular to the direction of the sound wave. Perpendicular to the direction of the sound wave. Perpendicular to the direction of the sound wave. In that sense, we say I, which is intensity, is equal to sound energy all over area times time, which is equals power over area. So the SI units can be watts per meter square. How do I get power over area? How did we deduce that sound energy over area times time is equals power over area? Yes, anyone? Energy over time is power all over what? Area. Abi? Now power is measured in watts. So we have the SI unit of intensity to be what? Watts per meter square. Is there any question? Any question? Now put this down. Intensity. Next class I'll ask question. Okay. No, we'll meet next week Sunday. I'll ask questions. Relax, don't prepare. If you did not get the question next week Sunday, you just leave the class. You get the question. Good for you. Good for you. You'll be able to sit down in the class. Yes, now you sit down in the class for the next topic. Oh, that's not it. Ayana. Oh, so I should share one iPhone because you read your book. I want that. I fasting. Oh, I wish to fast. I will do it. No. Oh. There's fasting. Both Lent and what? Ramadan. So fasting while everywhere. So what are you? Alright, I said write this down. Intensity depends on one. Intensity depends on one. Intensity depends on one. Frequency of vibration of the sound. Frequency of vibration of the sound. Frequency of vibration of the sound. 2. The square of the amplitude of the sound wave. 2. The square of the amplitude of the sound wave. The square of the amplitude of the sound wave. And 3. The distance away from the source of sound. The distance away from the source of sound. From the source of sound. Distance away from the source of sound. So from that we can say intensity. Hello. Intensity is inversely proportional to the square of the what? Square of the what? Amplitude. But here we denote amplitude as small r. We denote amplitude as what? One over r square. So we can say from here we have I to be equals what? K over r square. So if we have two medium and two amplitude, two different amplitude, we can say K is equals I r square. Abi. For two medium, it is what? I1 r square is equals what? I2 r2 square. So this formula, take note of. To be yellow, ni? Just forget about it. So put down this question. Put down this question. Let me see you. Let me see you. Let me see you. Let me see you. Aha. Put down this question. Hello.
Hello.
Yellow. This one. At one point, she was at maximum placement from year to year, from year to year, from year to year. Just like wave. Wave. Now, she's at rest. Load. Maximum potential energy. Ojo kò síbẹ̀. The intensity of a sound. Hello, put down this question. The intensity of a sound. The intensity of a sound. The intensity of a sound. Write this question down. The intensity of a sound when the source is 3 meters away. The intensity of a sound when the source is 3 meters away is 100 watts per meter square. Is 100 watts per meter square. Full stop. What is the intensity? What is the intensity when the source is 5 meters away? I believe you can do that. What is the intensity when the source is 5 meters away? Apply this formula and tell me your answer. Apply this formula and tell me your answer. Yes, yes, yes. Hmm. 60 watts. Okay. Cheese. Alright. Yes, any other opposing answer? She's correct. 166.7. Oh. 36. Why are you not getting 60? 166. She's correct. Yellow. She's correct. So what were the parameters given? Hello? I1 is equal to what? 100 watts per meter square. R1 is what? 3 meters. R2 is what? 5 meters. So applying this formula, we have I1, which is what? 100 times R1 square, which is 3 square, is equals I2 times 5 square. So we have what? 900 equals 25 I2 divided by 25. I2 is equals 36 watts. Watt per meter square. That was some meter per second, man. Yellow. All right, take home assignments. Yes, it is a must. Just answer true or false. You write true or false at the front. Oh, really? AI? Oh, con yellow ni. Ìwà ò pure. O ti ń pariwo AI. Like I said, it's true or false. Alright. It's a problem. Either ways, I will give you. And if you use AI, I will know. Because I also have AI. Don't worry. I will know. When I call you and you answer true or false, you now explain why. Yeah, no problem. The first question. Sound travel faster in air. Sound travel faster in air than in still. True or false? I don't know. Number 2. Sound is a mechanical and transverse wave. Number 2, sound is a mechanical and transverse wave. True or false? I don't know that one. No. Number 3, sound. Are you guys following me? Number 3, sound can be reflected. Sound can be reflected, refracted. Sound can be reflected, refracted, diffracted, and polarized. True or false? I don't know. Sound can be reflected, refracted, diffracted, and polarized. True or false? The next one. The next one. Sound can be produced. Sound can be produced only by a vibrating object. True or false? Sound can be produced only by a vibrating object. True or false? The next one. Sound can be transmitted. Hello. Sound can be transmitted through any material substance. Just put true or false. You don't need to understand. Just put true or false. You don't need to understand. When we jam in the next class, you understand. I said sound can be transmitted through any material substance, whether gas, solid, or liquid. Sound can be transmitted through any material substance, whether gas, solid, or liquid. Answer true or false. Sound is a longitudinal and electromagnetic wave. True or false? Sound is a longitudinal and electromagnetic wave. True or false? Sound, another one. This is number what? Okay, once it's number 10, we'll stop. Number 7. Sound cannot be propagated through a vacuum. True or false? Sound cannot be propagated through a vacuum. True or false? I don't know. But next week, the mode I'll use to answer this question or collect the answers from you will be different. I don't know. Like, write it down. Be like, look at it. I don't know. That's why true or false. I will meet next week Sunday. Yes, sound travels. This is number 8. Sound travels faster in cold air than in hot air. True or false? I don't know. Sound travels faster in cold air than in hot air. True or false? Air. A-I-R. Air. Ear. Air. A-I-R. That is number what? Number 9. Sound travels with the same speed in air. Sound travels with the same speed in air. Regardless of air pressure, of the frequency of the sound. True or false? Even your AI will talk say, he never do you. Number 10.
Regardless of air pressure.
Yes, regardless of air pressure of the frequency of the sound. The last one. The last one, which is number what? 10. The following are examples of transverse waves. The following are examples of transverse wave. A. So if it is true, you put true at the front. Each of the options. If it is false, put false at the front. So A. Ripples on water. I said the following are examples of transverse waves. A. Ripples on water. Ripples on water. B. Sound waves in steel wire. Sound waves in steel wire. C. X-rays. X-rays. D. The stationary waves in a resonance tube. Stationary waves in a resonance tube. And E. Stationary waves in vibrating string. So this is where we come to the end of today's class. So those of you that are joining us on live, please share, like, and subscribe. Till next week Sunday. Thank you. Stop it.
Hey,